to another Monday seminar. We have Nathaniel Starkman here today to talk about Astropy. He's a developer of Astropy and specifically Astropy Cosmology. He's also his research also focuses on understanding stellar streams in the Milky Way and use that to constrain the dark matters in the Milky Way. And furthermore, I also learned that Nathaniel knows tons about cosmology over lunch. So if you want to talk to him about cosmology, this is also a good chance. And he's from the astronomy department next door. So you can get a lot of chance to talk to him as well. So feel free to take it away, Nathaniel.
Thank you. Yeah, so all that and to say, yes, I'm in addition to being a graduate student here, I'm also one of the core developers for Astropy, specifically cosmology as well as units. And it's on this I'm going to talk to you with all today. So I want to thank Professors Dick Bond, Dylan Zhao, and the CITA Visitors Committee for their invitation, as well as Dr. Claire Yi for hosting me today. So I'm thrilled to be here to talk to you about Astropy and cosmology. And this talk will be broadly structured in 3 parts. The first section is on Astropy Cosmology, the package as it exists right now. The second section is on interoperability between Astropy Cosmology and the rest of Astropy. And the last section is about the changing landscape of Python and the future directions of the Astropy Cosmology package. Okay, so part 1, the package. Astropy Cosmology is the core Astropy package for cosmology, providing primarily tools for computing background quantities. Because it lives directly within Astropy, it is often the, oh no. Oh. All right. All right.
Sorry, which one?
The bases, the beats, the top right.
Okay. Okay, so because it lives directly within Astropy, it's often the first cosmology package that new astrophysicists, like undergrads, encounter. And this was the case for me when I was an undergrad at Case Western Reserve University taking a cosmology seminar. This was how I checked all my calculations of like co-moving distances, age of the universe, to see that my answers were right. Uh-oh, did I get decoupled? All right. So while research requires more specialized packages, Astropy's cosmology's prominence and central location make it important. It also provides us an opportunity to build a more interoperable computing landscape in the future, where Astropy Cosmology helps coordinate as a central hub when moving between different libraries and comparing results. So with that, let's take a look at the package itself more closely. Freeze. So what do we see when we look at the API docs? It appeared to have frozen. Do that here. Okay, that seems to have fixed that. We see that, if we could have seen that Astropy Cosmology is what's called an object-oriented approach, which means that it embraces sort of Python's paradigm of having the object contain all of the physics as well as the methods on it. And then what you use is the object rather than a set of functions that are contained within the library. So for those that don't write a lot of code, what that really means here is everything we need is contained on the object itself. I personally find this very intuitive. It means that when we're looking at a cosmology object, we know 2 things about it. One is its class encodes all of the physics. So if you're looking at a flat lambda CDM object, right, you're looking at a flat lambda CDM physics. And then since you're looking at an instance of that class, you're looking at an object, how it was created sets the free parameters. That means it specifies what cosmology realization we're working with. So we can see on all my animations and content appeared to be not rendering or sharing with people. Maybe I just reshare. I have a backup of this. Here we are. Maybe this goes faster for people. Perfect. Okay, so we can see that the cosmology class encodes the physics. We can see this in this inheritance diagram here, where you can go from a cosmology object all the way to a flat lambda CDM, each time specifying more and more specific physics. So FLRW metric to a lambda CDM to one that's constrained to be flat. And the second bit, which is the free parameters specifying your realization, we get when we make an instance of this object. So in this example, we're making a lambda CDM background cosmology, and we're putting in H naught is 70, omega matter naught is 0.3, dark energy is 0.7, and we get out a realization of our cosmology. And almost everything we need is on this cosmology realization, whether it's an attribute like some of the other omegas, or whether it's a method like the differential co-moving volume as a function of redshift. Right, so just simplify, right? We have on any object, we have its attributes and its methods, which contain all of the relevant physics. Most of the time, you don't need to make your own cosmology object. Probably you're just going to be working with a built-in realization. So we provide many of the standard parameter measurements, whether it's WMAP all the way through Planck 18. If you're looking at the docs, you can see this nice table. If you are in an IDE, then you can just look at cosmology.realizations.available to see all of the prepackaged set of cosmology realizations. So just to take a look at one, in this case, Planck 18, it's the most convenient one to use, most recent measurement. You can see that Planck 18, right, the method, because it's flat lambda CDM, gives us a flat lambda CDM cosmology with the Planck 18 measurements. And so we can do things like plot and show the differential co-moving volume as a function of some redshifts. Right. Oftentimes, it's nice to compare some set of cosmologies that are pretty similar. We have a method on every object called .clone that allows you to override any parameter value, keeping anything that's not specified the same. So if you want to look at Planck 18, but for whatever reason, omega matter really should be 0.4 and omega baryon 0.3, right? Then we can do that. And you can see the difference. Omega matter has changed, omega baryon has changed, and everything else. In particular, for example, the neutrinos has all remained the same. So this allows us to very quickly perturb any cosmology realization to get to another one. So we can, for example, look at a comparison between Planck 18 and that new cosmology, just looking at, for example, here, a difference in their age. Planck 18 gives 13.7 gigayears. This one that I made comes out to be roughly 12.8 for how old the universe is currently. In addition to working with flat lambda CDM, we offer a number of convenient dark energy models. So flat lambda CDM is what Planck 18, all the WMAP realizations are. But if you want to work with anything from a very simple, just not minus 0.1, you can work with WCDM or flat WCDM, or sort of iteratively more free parameters to specify your dark energy, all the way up to one with a pivot redshift in addition to the scale. So a variety of convenient dark energy models. And these are all of the most common ones that often appear in the literature. And they all have the exact same API, transverse co-moving distance, or whatever, H method. So it's very easy to work with all of them. You can just see here a very quick comparison. I just took the exact same set of parameter values from Planck 18, and then just added one thing or two things to specify how the dark energy should behave. In addition, it's incredibly easy to define your own dark energy model. If you want to add quintessence or anything under the sun, all you need to do is subclass the main class that people work with, which is the FLRW one, which gives us that nice metric. Write your own method specifying the dark energy as a function of redshift, and you can then add on any free parameters you want using our parameter class. It's as easy as that. I mean, when I do testing and stuff for Astropy Cosmology, it takes me a minute or so to translate a paper generally into a new dark energy model. We don't add them because we just want to keep it nice and atomic, but it's very easy to go from the literature to playing around with the new dark energy model. But the real power of Astropy Cosmology is its deep integration with Astropy units and something called unit equivalencies. You may be familiar with this if you used Astropy at all, right? Units allows us to have not just a number, but also the unit. And when we perform any type of calculation, the units get propagated through very conveniently. And cosmology, this most obviously appears in the fact that all of our attributes and methods return unitful numbers. So H naught comes out as you'd expect in kilometers per megaparsec, kilometers per second per megaparsec. The distance modulus out in magnitudes. So this is the very obvious surface level, but perhaps I think that's much more cool and exciting is that Astropy Cosmology actually has its own units and cosmology-specific equivalencies that aren't in the rest of Astropy for working with specific things in cosmology. So we can see here the API page. I'll dig a little bit into this, and not to short shrift little h, but I'm just going to be talking about the redshift unit and some of its equivalencies. Right, so redshift isn't a real unit. Why would we want to work with it? Pretending like it is. Oh, shift back. Well, for one thing, we get all of the nice things that Astropy quantities bring in terms of some of the convenience in plotting, but that's not so important. It's also nice that when you put in a unit of redshift, right, you get out the correct things in cosmology in megaparsecs, but we got that without units. Why do we want to work with redshift units? And the answer is unit equivalencies. So normally, we can only translate between two units if they have equivalent physical types, right? They have the nice same dimensions, length to length. But equivalencies allow us to convert between quantities that aren't of the same physical type, but in some context should be and are interchangeable, right? So if you were to try and convert that redshift, which has units of redshift, to megaparsecs, it's going to tell you it can't do that. They're not the same. But if we use this equivalency, redshift distance, we're saying that we know how to translate from units of redshift to units of distance. In this case, the default one is co-moving distance, but we can specify other ones like luminosity distance, etc. So to see that in action, here I'm asking it again to go from units of redshift to units of megaparsec. And I'm telling it, you know how to do this using the redshift distance equivalency. We can do this on a per function basis. So we can go from here from units of redshift to units of distance, also vice versa from units of distance back to units of redshift and these otherwise incompatible units. And something interesting to notice and important to notice is that the equivalency is actually cosmology dependent. So in the example I was doing, we were using implicitly, because I didn't tell it what it was, the default cosmology in Astropy, which is Planck 18. So distance to redshift, my nice contrived example should come out to 10, and it does because we're using Planck 18. If we switch over to WMAP, we can see that the co-moving distance translation, right, is different because the parameters are different, and so we get a redshift of 9.7. What's also nice is we can work within a context. So rather than specifying every single time we want to do, from redshift to distance, from distance to redshift, this equivalency, we can set a context for the equivalency, and then anything within this context automatically knows how to do these translations. So if you want to go from redshift to distance, from redshift to CMB background temperature, from redshift to Hubble units, it knows how to go through one of the cosmology instances, whichever one is set, in this case Planck 18, and it can go back and forth in either direction. So this is really, really, really convenient, right? You're probably reading some paper, it's in natural units, you're like, oh my gosh, is this in units of C, units of like blah, like yeah, natural units don't ever specify units, it's really hard to follow. You don't have to follow it, right? You put in your numbers and you're like, oh, they've just done something that converts from redshift to distance. I don't have to worry about this either. I can just go right from one to the other. So it allows you to write calculations much, much more how you think about them when working with pen and paper. So that's one thing that I really like with this. So just as a simple worked example, I just want to compare what happens when we perturb a cosmology over a large set of parameters. I'm going to be changing just like omega matter and omega baryon. And I'm just starting with a luminosity distance, and I want to plot how changing my cosmology affects the redshift that comes out. So here you can see I'm just making an array of my luminosity distance, imagining that's some measurement. I can very easily just make an iterator over minor perturbations to Planck 18, just adding a plus little delta matter right there, and then just enumerating over it and converting from distance to redshift, specifying that I'm using this equivalency. I could have embedded this in the context and gotten rid of that line inside of the for loop, but this is just nice and explicit. So you can see how I can very quickly go, oh, got cut off a little bit as a function of redshift for luminosity distance and explore small changes in your parameters. Very, very easy, combining clone and the redshift distance equivalencies. All right, there is so much more to talk about within Astropy cosmology itself. Could spend the whole hour on this, but I also want to talk about a variety of other things. And so we're gonna move on to the second part of this presentation, which is showing how Astropy cosmology can work within the larger Astropy framework. So here we are. Okay. All right, so the first thing I want to talk about is Astropy coordinates. Coordinates is one of Astropy's really core libraries that sees a lot of usage, and it's how we can represent coordinate data to do transformations from some simple things like spherical coordinates to Cartesian coordinates, but also much more powerful things like attach reference frames. You want to go from an ICRS coordinate to a galactocentric coordinate to a galactic LSR coordinate. It handles all of these reference frame transformations as well. Part of the mechanism that it uses to do this is the distance class. I think it's still working. So if you just is the distance class, which builds off Astropy units quantity. Oh no, this made it very small. Is that better? Yes. Astropy distance quantity to work with distance specific things. So we can see here it's made very similarly to a quantity, distance 1 units of gigaparsecs. But what it's nice about it is rather than just being a plain number and unit, it gives us access to a whole bunch of nice convenience methods, one of which is the distance modulus. Another is the redshift, which interprets the distance as a luminosity distance. That one's not configurable, it's always a luminosity distance. What's really nice though, is this actually has the units of cosmology redshift that I was just showing you, which means we get to use all of our convenient equivalencies. So we started by defining something with 1 gigaparsec distance. We converted it to a redshift through our luminosity distance conversion. And now that we have a redshift, we can exploit all of the equivalencies, for example, to go to CMB background temperature. So this is using the redshift temperature equivalence. And distance, which therefore cosmology, is very tightly integrated with the rest of the coordinates framework. So if you've ever made one of these low-level objects, which maybe you haven't, but we'll bootstrap our way up to more sophistication. So this is an example of spherical representations. We can go from like Cartesian to cylindrical. It's nice, you just don't need to pull up Wikipedia every time to forget where, remember where the square roots are and stuff like that. The distance of the spherical representation, right, is the distance object. So we can go right from working with some spherical representation on the sky, for example, all the way out very, very quickly to CMB redshift temperature, just like this. Our object to the distance, to the redshift, to the CMB background temperature. Chances are you're more familiar with stuff like the ICRS or the SkyCoord classes from Astropy, which is how we represent reference frames in addition to the data. So I've made here an ICRS representation of the Virgo cluster. Probably don't know those coordinates offhand. Right, it has roughly a distance of 18 megaparsecs at this position on the sky. Right, well, under the hood, the ICRS mechanism in Astropy, same thing as the SkyCoord, that one actually packages an ICRS, right? It contains one of these lower level representation objects, right? And those representation objects hold the distance class. And so again, we can go directly from, grabbing some data. I used one of the convenience methods here. I went, from name Virgo cluster, and so just grabbed it off the internet. And we can go right to what the redshift of the Virgo cluster is, assuming we're like in the Hubble flow and stuff like that. And of course, that means, again, we can go right to any of these alternative distance measures that we can get through the redshift. So I keep on returning to the CMB background temperature. That's just a nice, easy one. So if you were looking at something that's redshifting away from us, at roughly the distance of the Virgo cluster, where you expect a 0.01 difference in the CMB background temperature. And it's as easy as this, because all of these building blocks are built nicely on top of each other. And so we can go directly from looking at a coordinate object on the sky all the way out to any of these calculations. Yeah. Yes. That one you do have to know. So if you want to use just the .z method that uses the luminosity difference, if you do like 2 redshift, it sort of like tells you a bit more. If you want to do anything else, right, of course, you can just use Planck 18 dot co-moving distance, for example, and then use c dot distance, and then it'll do it. But yeah, it uses luminosity distance. All right. So that was showing just how it integrates into coordinates. Next, I want to talk a little bit about serialization, which is just saving objects to long-term storage. Right? It's incredibly important both for computing, but also for sharing results and doing good science. And one of the ways I've grown the cosmology package these past few years is to significantly expand the options for serialization and to build frameworks for people to easily add their own. And one thing we're working to do is continue to expand this. So one of the most dangerous, but also one of the most useful methods is something called pickling, which you may or may not be familiar with. I just want to say from the outset, do not use this. If you are using this, you should know why you're using it. And the reason probably is because you're doing multiprocessing with Python, which, because Python's multiprocessing is a little bit of a mess, you often have to pass data between threads. And the way that in Python this works is you pickle an object, which basically means you render it into a completely inscrutable byte string. You pass it from one thread to another, and that thing unpickles it, and then you're working with stateful data. So this is just showing in Python how you can pickle a cosmology and unpickle it. And what you get out is exactly equivalent to what you put in. So if you're using this, you probably know why you're using it, and that's good. If not, what you should be using is our serialization framework. And this is coordinated through the read and write methods on cosmology classes and objects. So if you cosmology class dot read, you can read a cosmology from disk, and you can then write one as well. So the currently available formats, the ones that I've put in so far, are ECSV and HTML. What is ECSV? Well, ECSV is a CSV format. So this allows us to just, comma separate value out all of the parameters, but it also allows us to attach arbitrary metadata. And this screen isn't quite big enough, but here's the actual list of cosmology parameters, and here's all the metadata telling it that, I'm a flat lambda CDM cosmology. This column, it has units of megaparsecs or kilometers per second per megaparsec for the H0 column. And so that means we can very nicely fully round trip all of our information with units attached. I mean, it's much larger in terms, I guess, of number of lines, but it also can't be hijacked for attacks, right? You can unpickle and people can break your computer. So I guess efficiency, safety. Also, this thing is pretty much independent of, right? If you were to uninstall Astropy and reinstall, your pickle would probably break. So this is actually good for long-term storage. Pickles just for short-term. So it's as easy as just writing it to this. Yes, so there are two commitments layered into here. One is the ECSV commitment. ECSV was actually created by Astropy in conjunction with like STSCI, and at the time Hubble. Now JWST is one of the people, the member organizations of this standard. And so there are a couple of iterations now of the ECSV standard, and they are all either backwards compatible or have compatibility easily built in. And then building, so I built on top of that this read write, and yes, we are committed to having backwards compatibility. So far, we haven't seen an evolution necessary, but when we do, it'll be able to read both. So yeah. And so we can also then read from this file. So that file I just made, plonk18.ecsv, we can read it out. And because we got to attach all of the metadata, our object, oh, sorry, that should be equals true. I just evaluated this. Oh, you can see 51 versus 135. This is actually a live Jupyter notebook. So it's just from a different load. Trust me, if you were to press restart run all, it would say true, that the original cosmology is equal to plonk18. Some of the later ones are like a plonk15 things. That's presumably what's going on. So that's probably the most useful one. I just recently put in help. Me and a contributor, we worked to put together to put in the HTML format, and that's mostly useful for putting your cosmology into like a website if you want to talk about it, or an HTML-based presentation like this one. So you can write out your file to HTML, include LaTeX strings, and then visualize it, share it, and then read it back. There we are. So we have two serialization options, and it's very easy to add new formats. So if anyone is interested, one of the ones we are most looking forward to trying to accomplish are a reader and a writer for CAM and class INI files. So you can just go directly from a CAM INI file directly to an Astropy cosmology. Should be very useful. Yes. Yeah, the Python CAM. Yeah, but that still reads the INI file for the initialization. Okay, so in addition to serialization, which means writing to disk, we also offer a powerful framework for live converting of objects to and from other Python objects. And that's the object interchange protocol. So rather than read and write, we have from format and to format, which means you can read an object into a cosmology realization or vice versa, convert a cosmology realization to another object. And we have a variety of available formats, which you can list out just by doing any cosmology.toFormat.list formats, and then it lists all the options. I'm just going to talk about a few. The first one, and sort of the base one, is the to a Python dictionary. So you can Plonk 18 to format mapping. I just popped the metadata out because it was long. And you can just see all the bits and pieces that make up a Plonk 18 cosmology. Like, why is this useful? The Plonk 18 thing had all this thing on it. Well, the way I actually showed making all of, in a previous plot, making all of those different dark energy models where I just sort of changed one thing. Well, this is actually how I did it. I just popped my Plonk 18 to a dictionary, and then I just add on any little bit of information, in this case, just a piece of information about the dark matter, and I can turn my flat lambda CDM cosmology into one that has more interesting dark energy. It's exactly the same as my Plonk 18. I just gave it whatever omega naught, W naught I wanted to change my dark energy. Yeah. Sorry, what? Which one? Oh, yes, this is Python 3.9 plus dictionary concatenation. So it just takes this dictionary and updates it with the contents of this one. And then since they start from format, we got out a new cosmology realization with a Plonk 18 parameters, but different set of physics. Makes it very, very easy, kind of like .clone, but that only allows you to change within the same set of physics. With this, you have all the freedom you want, and you can go between even different physics specifications. Right. All right, so that was to and from a dictionary. We can also go to and from a table. Here I'm, as an example, making a table, but chances are you get this from a paper somewhere. You know, they've listed out all of their parameter values. So this is what I'm imagining a table might look like. Someone has very conveniently provided the name, but they don't have to, right? It's all of the parameters that compose the cosmology. Well, we can very easily read from that table. There's a lot of customizations, which I'm alighting over, but in this case, just because we have the name of the cosmology, we can just grab the specific row and read out all that information. So you can go very quickly from tabular forms of the information directly to a realization and then work with it from there. And this last one is one that is in development a little bit. Some parts of it are stable, some parts not, but I think it's pretty cool. And that is to directly convert a cosmology object to an Astropy model, which is the Astropy's built-in framework for doing model fitting. We have hopes to go into other model frameworks, but this is just the one we're starting with because it's built into Astropy, so there's a lot of in-house expertise. So with this translation tool, we can actually take any cosmology and turn any one of its redshift dependent methods into an Astropy model. I just want to say that the neutrino bit of it is currently a little bit broken now, so that part will just fail. So I'm just going to turn off the neutrinos in this example, and effective equals 0, away goes our neutrinos, and I turn it into a model with just .2 format specifying which redshift dependent method is going to make the model. And so what we have out of this is an Astropy model with the fiducial set of parameters from the cosmology realization, right? So this will take as inputs redshift and spit out as outputs luminosity distance, and then we can do things like model fitting. So just as a simple example, I'm going to perturb this model, say that's the real truth, and then we're going to fit for that model. So here's our luminosity distance model. The real model has H naught of 70 and omega matter naught of 0.32 instead of 67 and 0.3, and just make a fake set of, or real set of measurements here. So this is the luminosity distance, given that's our model in megaparsecs. And now we can fit for the model given the data. So I'm just importing from Astropy modeling a simple least squares fitter, asking it to fit our model with H naught of 67 and omega matter naught of 0.3, given some set of, this set of z's and the luminosity distance. And we notice that the fit value it returns has h naught of 70 and omega matter naught of 0.32, exactly what it should have if it was successfully fit, which it has. The initial guess in blue changed over to the orange in, you can see here, which exactly overlays that fake set of measurements I made. So this is just a toy example of turning a method on a cosmology into a fittable model using Astropy's modeling framework. So we're hoping to shore up some of the bits like the neutrino physics. If you're interested in contributing, that would be splendid. All right. Last but not least, I want to talk about some of the ways that Astropy cosmology is growing. You saw one of these things in the development of this modeling translation, but there's a variety of interesting ways that we're looking to grow the cosmology package to help it be more important within the computing landscape and to also take advantage of the changing landscape of Python. So while the rest of these examples are all from a Jupyter notebook that I'm running right here, which means if I share it as a gist, which I probably will, you can just press run and it'll just work. Just warning, these following will not run on your computer as it requires some of my private Astropy in development tools. So the first thing is shifting away from just doing CPU-based computation, right? Currently, quantity, one of the fundamental things in Astropy, is built on NumPy ND array, which is a fantastic thing, right? It has enabled so much good science, but it's a CPU-based array. You can see that here. And the Python array landscape has changed dramatically in just the past 5 years, really. In addition to things we're probably familiar with, which is Python's built-in array library, which is trash, to the pandas data frame things, which has existed for a while, but is only now starting to get better. It's been joined by all of these really excellent tools, JAX arrays for doing machine learning and auto differentiation and just-in-time compilation and XLA, function compression to get incredible speeds. CuPy ND array to do GPU-based computation, Dask arrays to do parallel computation, cloud computation, sharded computation, larger than memory computation. A Z array for doing chunked and compressed things on the CPU, but you can still do work with much larger than memory arrays. And that's just to name a few. There's more. Right? It would be amazing to try and take advantage of all of that, both in Astropy and more generally also in cosmology. So if we think about what quantity is actually made out of, really it's just two pieces. One is the value, which currently is just a NumPy ND array, and the second is the units, right? And the magic of quantity is it knows how any operation on the value also affects the unit, so it can propagate that through the calculation, right? You're probably familiar with this. If I had to make a NumPy array, put into a quantity, you get out a NumPy array, you can do your computations on it. The next generation of quantity, and this is one of the things that Astropy is paying me this year to think about and try and develop, is to shift away from the value having to be a NumPy array, but really to be any array-like object. We get to keep all the unit magic for the unit propagation. So as an example, and this works on a development branch, we can take a JAX array, put it into a quantity, and then be able to do JAX computations on this. Take gradients through with unit propagation. Auto differentiation, do XLA compilation, though that one's still in development. That one's a little bit more challenging to do with unit propagation. But the idea remains, right, to be able to take advantage of all the amazing things that JAX offers for like machine learning and for very fast computation, and to keep all the convenience of unit propagation. And if we carry that forward, yes.
Can you briefly describe what the challenge is, or an example of what one of the propagating?
Yeah, so the way these things work for NumPy has a protocol for overriding any function call. If you do it, it asks, hey, do you know how to do this? And quantity says, yes, I know how to do this. And so rather than NumPy doing it itself, Astropy does it for it. Many of these libraries offer either very different or don't offer these types of overrides. And so making these things work with any one library is often a significant difference from how it works with NumPy, and making it work with every library, as you can imagine, is trying to fit not just, one rug into a little too small a room, but to fit, dozens of rugs into that same room. So it ends up being, even if conceptually simple, in actual implementation, extraordinarily challenging. But if imagining this, which kind of works in development branches, if we carry it forward to cosmology, what that means is we can be working with like a Planck 18 realization. We can evaluate with our JAX quantities, right? And you get out a JAX quantity, again, with units of megaparsecs. So what happens as an improvement to Astropy quantity can carry forward through anything that's in the Astropy ecosystem, including cosmology. Or as another example, which works very nicely, is Dask. So here I am making an array of redshifts from 0 to 10, and I have 20 billion of them. It's much bigger than I can carry just in memory. It's a nice big file on my computer. And I can carry this through in operations, and again, in calculations with cosmology. So this is what we're working on, right? Probably wouldn't run this on my computer. I didn't. That's why I wrote a really big array, right? But if you're running this on a supercomputer, or you've rented time on AWS, it can hold a 20 billion number array, and it can then do these calculations. And the second thing I want to talk about is an effort to try and unify some of the cosmology landscape. And that's something we're calling the Cosmology API. It's myself and some collaborators in UCL working on a protocol for a protocol to provide a unifying API so that we can build tools that work with any cosmology library, not just Astropy, but also CAM, class, and CCL. You build one function and it works with all of them. So from cosmology.api, we just import the standard cosmology API. This is like a FLRW type object from Astropy. Right, I'm just going to look at the API here. We see all the list of methods on it, right? Many of these look familiar. If you're familiar with Astropy Cosmology, I've put Astropy Cosmology here. In fact, they're pretty identical. And that's because it's based on the Astropy Cosmology API. I don't know, maybe it's something to do with because I'm involved with that. But the important thing is, despite it looking like Astropy Cosmology in terms of the API, it does not depend on Astropy. Right? If I had to import any Astropy Cosmology and I had to ask, is this standard API standard a subclass of anything in Astropy Cosmology? The answer is no. Instead, we're using Python's newish protocols, which allow us to build an API framework without specifying any of the implementation. So we can talk in abstract about how this thing should look without having to say how it actually functions. So the functioning is on the specific implementer's side, so Astropy Cosmology, CAM, class, CCL, and the way it all looks is specified by the API. So Astropy itself isn't yet conformant to the standard. So it's just reversing the question. What is it missing? Well, currently it's just missing something where the skill factor today, which for Astropy and for most other tools would just be always return 1. But for anything that's not conformant, we can have a compatibility wrapper. So for Astropy here, this one's very easy. This is just a mapping between the method in the API to the actual cosmology implementation. So making just using the wrapper, the Astropy standard cosmology here from the compatibility library. Now we get out something that is conformant to the standard, and we can evaluate any of these methods, right? The method in the API and this wrapper maps just to methods on Astropy cosmology objects. And in this case, we get all the convenience of units. The CAM one is still in progress. It's mostly functional. So I'm just making, just doing a little CAM computation, importing the compatibility wrapper. And again, right now, this is an object that is conformant to the API, which means that it has the exact same interface as the Astropy compatibility one as well. It goes a little bit further. Not only do you know what everything that's on the cosmology object, but you also get to know about the actual library as well. So anything right now that is hard-coded in is just that you have to have a module called constants, which specifies C and G. So we get to know exactly the API of the cosmology objects, but also how a little bit of how the library looks. And this allows us to build completely library independent functions that'll work with absolutely anything. So for some example function, my function takes a cosmology. Since we're using the API, we know exactly what this looks like. If we were to put in the Astropy wraps object, the CAM object, right? It doesn't matter. We can quickly change it out. And more than that, we get to always have confidence in a little bit of the structure of the library. So if we need to multiply by G, we know exactly where to find that in a library independent or package independent way. And this is incredibly useful. This doesn't guarantee the physics, right? CAM has slightly different physics than class. It computes things differently. You still need to worry about how CAM handles things versus class handles things. But what you don't have to worry about is someone asks you, oh, have you tried this with class? And you're like, oh my gosh, I need to rewrite every single function call, looking at their library documentation, figuring out, like, they don't call it co-moving distance, they call it co-move dist or something like that. It just takes away completely that worry. You just build your function one way and it works with every library. So that's where I want to take the cosmology API. Right now, it's just concerned with background computations, but the long-term goals of the API are to establish standards for many other things that are common in cosmology: power spectra, transfer functions, correlation functions, even looking at some non-FLRW type cosmologies. And to build out a nice standard so you don't have to worry about what specific implementation you're using. You can just build your functions in this very, very independent way. All right, so at the end of this talk, I just want to reiterate something, or maybe actually I think it's the first time I've said it, and that's that Astropy is open source, and that means it's the users that drive all the development. If anything in the way Astropy cosmology looks, sounds of interest or useful to you, you want to see it implemented now, or you think you have a nice new idea of how to make Astropy cosmology or Astropy better, right? We welcome and encourage contributions to Astropy. Right, that's how I got started with Astropy development. I needed something, so I just I forked the repo, made a change, submitted a pull request, and then a couple years later, here I am, somehow having been sucked into actually being one of the people in charge of Astropy. It can be a slippery slope, but if you don't want to spend all that time, you can just make small, meaningful contributions to whatever you think is useful. So thank you. That's a little look at the current and future directions of Astropy.
Any more questions?
First, I want to say thank you. I don't do cosmology, but I recently did a piece of your interpolated coordinates package.
Oh, nice. It is
not.
not.
But I wanted to ask what you think the total efficiency yield. Like if you were going to go back 3 years ago and do some cosmology research. This is a stupid question. Then you were going to go do some cosmology research, and you thought that then you had to like rebuild all of this from scratch. How much time do you think that would take, and what would be the total impact of?
Yeah, so there are metrics roughly for computing. It's like the code developer hours. and it's based on well, analysis of GitHub code repos. Building good software is really, really hard. Astropy is worth many millions of dollars in terms of actual salary if you were to try and pay people to do this. This is one of the nice things and terrible things about open source is we got many millions of dollars worth of work for much less than many millions. That's partly good, partly really bad. It means there's many, many people out there doing work that's under-recognized, whether that's in terms of actual monetary funding or in terms of academic recognition for contributing. So I think things like Astropy are invaluable. I could not transform between galactocentric and ICRS coordinates nearly so efficiently.
This attempt that you have a cosmology API and have these units propagated, are people beginning to use these?
Oh, in cosmology field specifically? Well, the API one actually has already seen some adoption. The collaborators I'm working with, they're the developers of GLASS. So they do a lot of lensing stuff, and they build high performance cosmology libraries and then want to compare their results to CAM. So they actually started this effort. And then I've been collaborating with them to take it to sort of the next level of code professionalism and to try and bring it to the big stage, so to speak. So yes, it has already seen uptick, and the ability to do JAX and DASC and stuff, things with quantity, that will help cosmology certainly. But that one also just will help everyone. I mean, plasma physicists use Astropy as one of their base libraries to do units. So it'll help plasma physics because they don't have their own units library. Plasma Pi, if you're familiar with it.
Jake, do you have a question?
Oh, yeah. So obviously there's an arbitrarily large amount of software out there, even buried in modules, etc., in codes, even some written in the august language of Fortran, as some of the people will groan at in the audience. And you know, one often does or wants to do Python wrappers for it. An interesting question is, I mean, the thing that's sort of concerning and great about this is that you need gatekeepers like you to ensure that whatever goes into what's in Astropy is appropriately ready for prime time in terms of coding style. That must be difficult because most people that do it would be doing it, flying seat of the pants or something, trying to get something that works. And then a step to actually make it something that it's injectable into the Astropy framework would require work that people might not undertake. So can you maybe expand a bit on the process between, let's say, somebody who's doing what I was describing and then turning it into something that would become Astropy-ish?
Yeah, so if you're doing Fortran or C things, right, we have some of those things in Astropy for high performance sections of the code that then get wrapped, bound into Python objects. But perhaps to the deeper point about you're working on a paper, you write a function that's useful in the context of your research, and you want to contribute it to Astropy, how exactly does that work? Right, this is actually one of the gaps that open source software struggles with, right? What I write for my research is, let's be honest, probably not great code. I try to write good code, but it's geared specifically to do one thing. And I may say that this, calculates the co-moving distance, for example. But if you would actually, analyze this mathematically, right, it probably fails if like the redshift is negative or something like that. And that's because in my project, I'm never going to have a negative redshift. I'm not going to be looking towards the future. But to take this then from personal code to production ready code that people around the world can use requires sort of from taking a back of the envelope calculation to a full paper. It's tough, it's challenging, it requires work. And that's something that makes contributing to open source challenging. You have to be willing to put in some of the time to take your function that was geared very specifically towards your needs and build it into something that's general enough to be used by people for a larger variety of contexts. Maintainers like myself will help you get over that threshold and cross that line, dot the I's, cross the T's, but it's still a process. Personally, I think it's very valuable. We write so much software these days. Most of the stuff I do, right, you start with pen and paper, and then you spend the next 3 months translating that into software stuff, and it's very ephemeral. When you take some of a meaningful part of your code analysis, right, and you turn it into a tool that becomes part of a community-wide set of tools, right, it gets baked in and checked at that time in a way that it doesn't perhaps ever if you are submitting something else. Who knows how many results that we think, oh, look, that paper's cool, but we can't really look at the code. We don't have time to really dive into all the nitty gritty bits of it. Who knows how much of that stuff is just wrong, and we'll never figure that out. So contributing to open source science makes your science better. It makes it harder to do because it's more work, but it makes it better.
Yeah, I don't doubt that. And maybe that should be part of everybody's training to do better code writing, but it's like putting in comment. Some people comment and some people don't bother with comments because they have it in their head. But here you have to have lots of comments, presumably, because you're basically doing a narrative for anybody using it.
Yeah, at Astropy, we strive to have pretty good code comments and lots of documentation. So detailed
Right.
doctrines.
And there must be, protocols for exactly how that's done. So is this written down as recipes that people can follow, or are you kind of a rate limiting step that people have to go through in order to?
So like in terms of the stuff I just showed today?
Well, not that explicitly. I'm still onto the issue of process, and whether if, let's say, somebody who works with me had done something Pythonish, maybe even with a Fortran or C underlying engine, would they be able to go to some place and say, if I did this, this, and this, it would then become something that might be compatible for Astropy rather than, just leaving it as it is, which is what your point is. And I think it's a very good one, that there's so much software that is sort of a once-off use and then it's never used again.
Yeah. Yes, we have in the Astropy docs a whole development section about how to become an Astropy developer, and that includes discussion of how to use GitHub, how to fork and modify the Astropy repo and make a code contribution. So we have some pretty detailed docs talking about how to make a contribution to Astropy. But then, yes, I am the rate limiting step. If you submit to Astropy Cosmology, my eyes will be on that bit of code to check it out.
And are you saying that although they're giving you a little bit of monetary support this time, you're doing this as all free labor?
Yeah, up until this year, where I got some funding both to be the cosmology maintainer, as well as to think about sort of the future of Astropy quantity. Yeah, it was volunteer work. A number of folks at Astropy are completely volunteers, but thankfully Astropy is in a rather enviable position in the open source community in that it has a lot of institutional support. STSCI pays a large number of people who work on like the JWST pipelines to do Astropy development because of how integral and important it is to all of their analysis.
Really neat. So then there's a whole operation going on, not that it hasn't occurred elsewhere, but CCA has really set itself up as a mission to try and help to be a repository with maximum use of software packages that have been developed all across Astro. Like Whelan, I think is the guy's name.
Yeah, Adrian.
Yeah. Is that integrated at all into the Astropy operation? Because it's more for, I'd say, high performance things, but it seems to me that it should be part of the generalized equation here.
Yeah, I don't disagree. So Adrian is one of the core members of the Astropy
That makes
team.
sense. Okay.
Yeah. Yeah, he's actually, him and a couple other contributors back in the day wrote quantity. So I've worked with Adrian a lot to do things in Astropy, and his personal package, Gala for galactic dynamics, is deeply integrated with Astropy. So one of the things that's of interest, you mentioned like the high performance computing, right? Astropy is not currently compatible with some of the most latest and cutting edge techniques, Dask, JAX, and stuff like that. So bringing Astropy on par with these new tools would really allow it to flourish in the high performance, big computation section of astrophysics.
Well, and even flourish with student uptake, because all students come in with really pretty good Python skills, or develop really good Python skills. And if it can sort of seamlessly go to the really, large computational programs, that would be just wonderful for the subject.
Yes, absolutely.
Yeah.
Maya,
Anyway,
do you have a question?
Yes.
Sorry, Maya, do you have a question?
Yeah, thanks so much. And yeah, thanks, Nathaniel, for the great talk. And it's great to hear about some of these new developments too for Astropy. And I definitely use Astropy Cosmology a lot for gravitational wave research, like just converting redshifts and luminosity distances. And I have a question which I might be able to find just by like searching the docs, which are also really well written. But one thing that I end up doing a lot is interpolating. Like I define JAX or NumPy interpolant to go from redshift to luminosity distance, because I don't want to have to like call something that's doing the integral every time. Is that part of, is that somehow like built in already to some of these functions so that it integrates with the units and some of the other benefits that you mentioned?
Yeah, so interpolation is something that we're very interested in, right? Right now, all the things you mentioned, these methods, they perform their computations element-wise, in this case, solving the integral for each one. Yeah, so we are looking to build a framework that changes this, so you have the option to work with interpolation tables. If you're interested right away in having, well, NumPy interpolation with units, I actually found this useful enough myself that I wrote a little package called interpolated units. If you're looking for splines, you can do any SciPy, like, interpolated univariate spline with full units. So you don't have to strip and reattach the units yourself. Here is the classic Witch of Agnesi with X in seconds, Y in meters, and it carries the units through the interpolation. So just maybe pointing you to that if you want to do some fast interpolations. This is the interpolated coordinates, which was mentioned earlier. So that's how it builds it. Just has an interpolation table for, I really should update this, for any of the objects. You can do full like coordinate transforms and have an affine interpolate.
Okay, yeah, no, this is awesome. Thanks so much.
Happy to help.
Questions? Now let's thank our speaker again.